Everything so far has been a piece of one problem. This lecture puts the pieces together. Satellite systems are built backwards. Engineers do not begin by choosing an orbit. They begin with the service the network must deliver, and with the handset that has to close the link. Take a requirement that occupies one line in a specification. Continuous voice to ordinary LTE smartphones anywhere on Earth. That sentence generates dozens of constraints. The smartphone sets maximum transmit power. Transmit power limits allowable path loss. Allowable path loss constrains altitude. Altitude sets footprint size. Footprint size sets how many satellites you need. Satellite count drives manufacturing, launch, and orbital maintenance. And antenna gain has to make up whatever margin is still missing. Which leads to the central lesson. There is no independent variable. Raise antenna gain and you may need fewer satellites, but the spacecraft gets heavier and costlier. Lower the altitude and the link closes easily, but the footprint shrinks and you need more planes. Add bandwidth and you need more electrical power. Add spectrum and you need regulatory approval. Engineering here is not the pursuit of maximum performance. It is the search for the best compromise. That reframes the whole industry. AST SpaceMobile, Starlink, and Link are not competing with different ideas. They are solving the same optimization problem with different objective functions. A useful way to put it, they all pay the same engineering cost, but in different currencies. AST pays in antenna aperture, Starlink pays in satellite count. Link pays in reduced service ambition. Side by side, the divergence is easier to read. AST flies few, very capable spacecraft near 700 kilometers, with regenerative cellular processing and an aperture heading toward 223 square meters. Starlink flies a much larger constellation far lower, around 340 to 370 kilometers, with smaller distributed arrays and a largely transparent architecture. Link flies a small constellation between 500 and 600 kilometers as a cellular repeater aimed at messaging. Now let us design one. Not a flight-ready system, just the sequence of decisions. The brief: standard LTE smartphones at 23 decibel milliwatts, global coverage, continuous voice, a circular orbit at 600 kilometers, a minimum elevation angle of 25 degrees, and operation in existing cellular spectrum. Step 1. The footprint. At 600 kilometers, a satellite geometrically sees an enormous area, but with a 25-degree minimum elevation, the usable service radius is only about 800 to 900 kilometers. That is roughly 2 to 2.5 million square kilometers per satellite. It sounds vast until you remember the Earth's surface is over 510 million. Step 2. Allowing for overlap, handovers, redundancy, and polar coverage. Continuous voice needs roughly 1,500 to 2,000 satellites. Step 3. Distribute them. A Walker Delta arrangement of 30 to 40 evenly spaced planes with 40 to 60 satellites in each gives fairly uniform revisit times and few regional gaps. Step 4. Close the link. Since the handset cannot exceed 23 decibel milliwatts, the satellite compensates with gain, a large digitally beamformed array, hundreds to thousands of elements, and multiple simultaneously steerable beams. Now change one variable. Raise the orbit from 600 to 900 kilometers. Immediately the footprint grows, and you need fewer satellites, real money saved. But path loss rises, propagation delay rises, the uplink margin shrinks. The antenna may have to grow to compensate, and capacity per unit area falls. Nothing here comes for free. Every improvement introduces a compromise somewhere else. Finally, 4 questions that sound obvious and are not. Why not use GEO? Coverage is not the problem, the uplink is. A 23 decibel milliwatt handset cannot overcome the path loss at 35,000 kilometers. Why not let phones transmit harder? Battery, heat, SAR, safety limits, and regulation. Why not just build a bigger antenna? Mass, deployment risk, thermal load, and diminishing returns. Why not move to higher frequencies? Path loss and rain attenuation get worse, and pointing gets harder. To close. Systems are designed backwards, from the service and from the handset. There is no independent variable. Every gain creates a constraint somewhere else. The same link budget produces radically different architectures depending on which currency you pay in. And there is no universally best design, only a different point in the trade space.